This presentation is with regards to hypothesis testing, specifically a flowchart. What you can do, you can take a screenshot of this flowchart and you can read through it, study it, and then you can go through it with the video. So as you can see, the first step is to state a pair of hypotheses. Okay, by now we know what is a hypothesis. The null hypothesis and the alternative hypothesis. Then you've got to state the significance level. That's a probability value called alpha, commonly used 0.05. That's a threshold value. And we'll talk about this in a little bit later on. Then you have to calculate what they call a test statistic. That means you have to use sample data and do some calculations, either manually or a statistical software can do that, called a test statistic. Then you got to obtain a critical value. This can be obtained via tables, or the statistical software can provide that for you. And then you got to obtain a p-value. Again, you can obtain that through statistical tables, or the statistical software can do that for you. Then you got to decide what approach you are going to take, either a critical value approach or a p-value approach. If you take a critical value approach, then you got to complete what you call a fully labeled distribution curve with the rejection region, the critical value, and the test statistic. So now we've got to use that distribution curve to decide to reject the null if the test statistic surpasses the critical value and is in the critical region or rejection region. So if the test statistic is in the rejection region, which is the shaded region, then you reject the null hypothesis. Otherwise, you do not reject the null hypothesis. So here's an example of a fully labeled distribution curve. Here, this is a normal distribution curve, commonly used for z-test and t-test for population mean. So here, you can see the shaded region is a rejection region, and the test statistic, here it is, negative 83.33. It is located in the critical region. Here you have the critical value, which is minus 2.33. So in a situation like this, you would have to reject the null hypothesis. Here's an example where the test statistic, negative 1.56 in this case, is not in the rejection region. So in this case, you do not reject the null. As you can see, the critical value is like a boundary line separating the non-rejection region from the rejection region. So in this case, because the test statistic is not in the critical region, you will not reject the null. Here's another example where you will not reject the null because the test statistic is not in the critical region. Here you have another type of distribution curve. It is skewed towards the right. This is normally used in chi-square test. You'll learn more about that later down. And the critical region or the rejection region is always on the right side. And here you have the critical value. And here you can see the test statistic is in the critical region. So in this case, you have to reject the null hypothesis. Obviously, as you can see, in such a situation, the null hypothesis will not be rejected. Once again, reject HO. Here, do not reject HO. That will be the decision. Here, do not reject HO. Here, you will decide to reject the null. And in this case, you will decide not to reject the null. Then you have what you call the p-value approach. So in this case now, you will simply compare the probability value with the significance level. So the probability value now will either be greater than or less than the significance level, okay, which normally use 0.05. So in decision time, you will decide to reject the null if the p-value is less than the significance level. And otherwise, you do not reject the null. So for example, if the p-value is equal to 0.33, this means there is a 38.3% chance that if you reject the null hypothesis, okay, and it is true, you'll be making an error. There's a 38.3% chance of that happening for you to be rejecting the null hypothesis, and it is true. You normally call that a type 1 error. So there's a 38.3% of chance of that happening. So this p-value now is considered large. The larger the p-value, the more the sample data supports the null hypothesis. Okay? So since the p-value is greater than the threshold of 0.05, which is the significance level, in this case, you will not be required to reject the null hypothesis. So once the p-value is greater than 0.05, once it is greater than the significance level, then you do not reject the null. So any p-value which is greater than 5%, okay? For example, you will not be rejecting the null, okay? Because in this case, for example, there's a 38.3% chance of making a type 1 error, which is high, whereby you'll be rejecting the null and it could be true, okay? So in this case, you will not reject the null hypothesis. Now let us say the p-value equals to 0.027. Okay, so this means there is a 2.7% chance that if you reject the null hypothesis, which is H0, and it is true, you'll be making a type 1 error. So there's a 2.7% chance of making a type 1 error. That is relatively low, okay? Because 2.7 is less than 5%. Okay, the smaller the p-value, the less the sample data supports the null. Okay, so since the p-value is less than alpha, which is the significance level of 0.05, for example, here you must reject the null hypothesis because there's a very low chance you'll be making a type 1 error. A small p-value means the sample data, there's a slim chance that the sample data supports the null hypothesis. So a small p-value, less than 0.05, less than the significance level, you will reject the null hypothesis. After decision is conclusion. If the null was rejected, then you'd have to conclude with the alternative. Otherwise, if the null was not rejected, you will conclude with the null hypothesis. Okay? Bear in mind, you're starting with two statements, the null and the alternative. So if you reject the null, that means it lost the debate. The winner is the alternative hypothesis, and that will be the conclusion. But if the null was not rejected, it has won the debate. So therefore, now it will have to be the conclusion.